Okay, so from worksheet 5.2, no, sorry, 5.1. There we go. 5.1b on number 35b, it says to find the particle's direction of travel. All right, so in order to answer that question, if you're trying to find the direction of travel, what quantity should we look at? Should we look at force, velocity, acceleration, displacement, position? Which one determines the direction of travel, you guys? The velocity, right? Right, because velocity is speed and direction, right? So to do that, here's the deal. The problem tells you that the velocity of the object at time t is this. It's 8.00 t in the I direction plus 3.00 t squared in the j direction. And the question wants to know the direction of travel when the net force is 35 newtons. So if you did part A, you found the time at which this occurs, right? Take a look back at your part A and see if you found the time for that to happen. While I grab my notebook and see what that time was. So what do we got? Chapter 5, number 35. Yeah. So when you did 35A, you couldn't have done 35A without finding out that the time was 1.415 seconds. Good? So all I'm going to do is I'm going to take that time and plug it into my velocity vector. And that tells me that the velocity at time t, or at 1.415 seconds, is I didn't write out the whole numbers, but it's so you're going to get this. Your Vx is 8 times 1.415, and then your Vy is 3 times 1.415 squared, whatever that is, and you're looking for the angle. So you just do inverse tangent. Good? All right. So that's the deal with 35. That's big. That's a second problem we've had, you guys, that we've gone over in class where you've been looking for the direction of travel and you got to find the velocity, right? So that's a big thing. Make sure you know that the direction of travel is determined by the velocity, not by force, not by acceleration, not by position, but by velocity. Clear? All right. Any problems with 35? Okay. What other one did I just say I was going to do? 60. Yeah, let's do 60. What's going on with this one? All right, so this is section 5.1b, number 60. All right, so you've got this this box. Recreate the drawing here. It's got a mass. It's being pulled with some force at an angle theta, some number of degrees above the horizontal. All right, we know that the mass of the block is 5 kilograms. We know that our force has a magnitude of 20 newtons. And that our angle varies with time. So the angle at a given time is, it wrote it out in scientific notation, just for simplicity, because it's easier to write. I'm going to write 0.0200 t. That's the same thing, just not written in scientific notation. Okay? And then what we're trying to do is we're trying to find the rate at which the acceleration of the block is changing. So we're trying to find the rate at which the acceleration is changing with respect to time. Does that make sense? That's what we're looking for. Everybody good? Okay, so, oh, I feel like I'm missing something. What other piece of information there? Oh, okay. When theta is 25 degrees. Okay, so we got to establish two things. First of all, we got to find out the time at which this occurs. Then we need to find our derivative at that time. Hello? All right, so let's find the time first. That seems like it's pretty easy, right? We know that our theta at a given time is 0.0200 t. So we can just go, oh, well, that's equal to 0.0200 t, and divide and find out that the time is, what is it, 125 seconds? Oh, I'm way off, aren't I? Teach me to do math in my head. 60. I hear people saying, oh, 1250, there it is. Okay, so there's our time. Is everybody good up to there? All right, now, in order to differentiate the acceleration with respect to time, we need to come up with an expression for the acceleration in terms of time, right? So let's see. The acceleration of the block is going to be the net force on the block divided by the mass, right? Now, this is a little bit sloppy because, oh yeah, what did we do? I'm sorry, I'm out of, we had already talked about normal force at this point, right? Yeah. Okay, good. All right, so it turned, well, regardless, the 20 newtons, there's no way that's ever going to be enough to lift this thing, right? Because this weighs almost 50 newtons, right? So there's always going to be a normal force. In other words, this thing's never going to come up off of the ground. So what force is going to determine my net force? What do we got? I didn't hear what you said. Oh, gravity? I gotcha. Well, so what, I mean, do you understand why it's not gravity? Yeah. Okay. What force is going to determine the net force, you guys? It's frictionless. The horizontal component of this force, right? So my net force is going to be whatever this force is times the cosine of the angle, right? So taking that a step further, our force is 20 newtons times the cosine of 0.0200 t over our mass of 5 kilograms, sorry. Does that make sense, you guys? All right, so 20 divided by 5, so that means that my acceleration at time t is just going to be 4 times the cosine of 0.0200 t. Oh?
That's kind of off topic. Does the sun have like any measurable?
Let me finish this problem, and then I'll come back to that. All right. All right, is everybody okay with how I got this? Right. It might be worthwhile too. Does everybody understand why we found that? Look, the only way that you can find the rate at which a value changes with respect to, in this case, time, is to come up with an expression for that value in terms of the thing that it's changing with respect to. That was a horrible sentence, but, right, we're trying to differentiate A with respect to time, so I need an expression for A in terms of time. Follow? All right, so now we just take the derivative. So let's see, A prime of t using sort of sloppy notation. So that's 4 times, what's the derivative of cosine? Negative sine of 0.0200 t times the derivative of 0.0200 t, which is 0.0200. Cool? So simplify this and you get 0.0800 negative style times the sine of 0.0200 t. And so that is, it's our derivative, it's the derivative of A with respect to t. I don't know why I used the prime notation there. But
whenever you're like changing force, and so it's like force is a function of time.
Yep. Yeah, that's chapter 6. Air resistance does that. As your object falls faster, the force of air resistance gets bigger, gets ugly. Okay, are we good? Well, and actually, I mean, that's kind of what we did here, right? Because the horizontal component of force is changing with respect to time. So that's exactly what we just did. All right, so now you just plug in your time and you're done, right? Because we're trying to find the rate at which the acceleration is changing at this time. So plug that time in and there's your answer. Cool? And then if you were confused by it, I don't know if this is something that ever came up, but on the answers I wrote jerk equals. That's like a physics term, right? The jerk is the rate at which your acceleration is changing. Yeah? Cool? And did I already tell you guys this? What's the rate at which the jerk changes? The snap. What did you guys say? Oh, okay. Oh, the jounce. Yes, yes. Now that you say that, I do remember that. Okay. So but the next three are snap, crackle, and pop. Yeah. Science. Yeah. What do you got? Well, then either I made a mistake or my answer on the answer key is wrong. Oh, fudge. Yeah, I totally forgot. Darn it. The answer on the sheet is right. I made a mistake up here. It's small, but it's a mistake nonetheless. Oh, shoot. All right, so here's where our problem is. The derivative with respect to t of cosine of t is negative sine of t if t is in radians. And that's something you may not have known. All right, the rules for differentiating sine, cosine, and tangent are assuming that your angle is measured in radians. So the time is fine, but I need to convert this 0.0200 degrees per second into radians per second. So, just because, so when you graph, the question is why does it have to be in radians? So if you graph cosine, it looks like this, right? And so it's, I don't want to say this, I don't want to go into a ton of math, but I mean, so here's 2 pi, right? So the idea is the derivative of cosine at 2 pi is 0, right? But that's not, I mean, 180 degrees. I don't want to say that. Sorry, I'm just trying to think of a good way to represent it, of why that has to be true. Let me think about it. I don't want to stand up here and just, you know. Let me come back to you tomorrow with a good reason for why it has to be in radians. Okay? There is a good reason, but I am not coming up with a real quick answer for it right now. But sorry. I think that's probably the only time that it's going to happen. Okay. Well, no, that's not true either. When we get to angular motion, it'll be almost always radians. So anyway, when that comes up, I'll let you know. All right. So yes, lesson. Write that down in your little list of tricks. Remember, when differentiating trig functions, make sure your angles are in degree or in radians. That almost was bad. Yeah, Alex.
So you would have considered series.
Yeah. So this formula here, this is in degrees per second times t. So 0.0200 degrees times, what is it, 180 degrees is pi radians. So our acceleration with respect to time should actually be 4 cosine of, and I wrote it as pi over 9,000, but I mean, whatever, you need to find a way to. All right, so that means that when you take your derivative, here, let me do it in red so you can see where I'm making changes. This 0.020 and 0.020 here both should have been, oh, fudge. So we got to differentiate this. So you got -4 sine pi over 9,000 t times pi over 9,000. All right. Yes. And that works. Now you can plug your timer. Yeah. Say that one more time. You're confused with. Like I said, I'll come in tomorrow with a better answer. Tuesday, Wednesday. Okay. Yeah. Till Wednesday. Yeah. Okay. All right. Are we good with that one little exception? Are we good with that? Okay. Cool. I'm sorry. I should have stuck closer to my notes, and I wouldn't have made that mistake. Okay. All right, so we got 35, we got 60. 61 and 83 are just algebra. And then 22, there's not a whole, I mean, you definitely need to think on that one, but the math on it isn't that bad. I'll put that one up on the website. I think we should probably jump to 5.2. Is that cool? Okay, so 5.2. Also, if anybody knows how to bleep YouTube, I should probably bleep out all my fudges. All right, what do we got? I can't see the board. All right, so what do we got? 7. $13. 16. I see 11. Is that? Oh, I see. 13 has a lot of votes. I see. Okay. So 13 and 16. Which one has more votes? 13. Okay. Yeah, 13 is actually a good one to do because it's something you definitely need to know how to do. So let's do 13. I think we get through it relatively quickly, and then I'll probably have time to do one more. We should probably talk about number 7 since it's concept-y and the answers aren't on the sheet. So let's do that, and we'll see where we're at on time. Okay, so here we go. So now we're on to section 5.2. What did I just say? Number 13. All right, and let me dig out my notes. Our time is important. I don't want to make another mistake. Where did I put them? Seriously, I just had them a second ago. Okay. So for number 13, we've got these 4, what are they, just masses? Does it say what they are? Discs. Ah, very good. Okay, so you've got so here's disk A, disk B, disk C, and disk D. All right. So it says the longer top cord loops over a frictionless pulley and pulls with a force of magnitude 98 newtons. So my tension here is 98 newtons. The tension in the 3 shorter cords are 58.8 newtons. 49.0 newtons and 9.8 newtons. And then you got to find the masses of the 4 disks. All right, a quick note about notation. I am religious about always putting an F in front of my forces. I think the book just uses T1, T2, T3, and it's sort of up to you to know that they're forces. I always, for every force, I always do capital F and then a subscript that describes it. So this means force. What kind of force? Oh, tension. This is the force from tension number 1, force from tension 2, etc. Okay. The book doesn't always do that. So just know when they use capital T, if it's in reference to a force, it means tension. The reason I don't like that is because sometimes T means period, right? So I try really hard to make sure that I'm really specific with my forces. Okay, so really, the idea here is we're gonna work backwards. We're gonna start at the bottom and work up. All right. So if you focus just on disk 3, or I'm sorry, disk D, the force of tension number 3 is 9.8 newtons. Tell me something else I know about this disk. We will know that in a second. You skipped a couple steps. What do you got, Kelly?
The force of gravity is acting on it, and it's 9.8
How do you know the force of gravity has to be 9.8?
because it's acceleration is 9.8.
Close.
If it's downward,
What's the disk doing right now?
it's
It's motionless, right? So the acceleration is actually 0, right? It's not moving.
Well, yeah.
And so the net force is 0, which means that the gravitational force has to be exactly canceling out the tension force, right? And therefore, now that you know your force of gravity, divide by 9.8 and get your mass of 1 kilogram. Make sense? All right, is everybody good with, that's block D, which I think is actually the last question. So you got to kind of answer these in reverse order. All right, so that's disk D. Are we good? Okay. Oops. All right, so disk C. So disk C actually has 3 forces on it. Gravity's pulling it down with some amount of force. I don't know how much. What are the other 2 forces? Tension, but there are 2 tensions, right? There's the force from tension number 2, which is 49.0 newtons, and the force of tension number 3. But we know what that is. What is it? 9.8. Follow? So again, we know that the thing isn't moving, so our acceleration is 0. That means our net force has got to be 0. So now I can figure out what this force of gravity is, right? Because 49 newtons has got to cancel out both the tension and the force of gravity. So this has got to be 39.2 newtons. And now you can find your mass, divide by 9.8, and it ends up being 4 kilograms. Yeah. There are other ways of doing this where you...
I just don't know if I'm really consistent like the word.
Did you treat block C and D as one thing? That works too.
It's kind of like I actually lower tension and then divide by 1.8.
I think that works. I would have to sit down and do some calculations. My concern is that that may only work if the acceleration is 0. And that's what I'm nervous about.
The word for this.
Yeah. So the way that I modeled it here is the way that I think that'll always work. You know what I mean? So I guess I would try to kind of follow it that way. Your way does work here, though. If it was accelerating, I don't think it would. I think it gets a little ugly if it's accelerating. So and there's actually a problem like that in 5.3. So it's chain links instead of little disks, but same idea. All right, are we good? Do I need to go through the rest of it? Okay. All right. So yeah, these guys are the same. All right. All right. So now we need to go back and get. Oh right, this Kansas City rods and walkways and dancing bands and problem, right? Okay. So what's that? Intricate setup. Yeah. Yeah, and I almost didn't assign it, and I think I was like 51-49. I was like, oh, and I probably should have opted no. But I remember reading this, and it left me with a lot of other questions, like, well, what's holding these things to the walls? And like, I just had all these other questions that were seemingly irrelevant. But so here's the gist of it, you guys. Check it out. So you've got these 2 setups. So in setup number 1. All right, so you've got these little like bolts or nuts or whatever that are kind of holding things in place. And then you've got, in the first example, you've got this one rod that runs up the sides. Okay, and so the way that it's worded, they make it sound like these, what do they call these? Do they call these nuts or bolts or nuts? Okay. So these nuts are sort of supporting the weight, right? So in any given situation, in any given level, like if there are people standing here, these two nuts here, these two red nuts, are supporting the weight just of this bar and this person, right? Similarly, that nut and that nut are supporting the weight of this person and this bar, right? Because this red platform isn't touching the green nuts at all, right? So does that make sense? That the first setup is, it's cool because each, thank you. Yeah. Because each nut is just supporting one level. So are we all good with that?
Yeah.
Right. That's not true in the second drawing. Where are you going? Is it raining? I don't know how to spell that, so this is Z. Oh, and I said hello. It is 2:55 in the PM. There you go. Yep. Does that go okay?
Yeah.
No, you're good. Okay, now in the second drawing, you've got this. Oops. You've got these red bolts here, right? So right now, those red bolts are supporting the top, about to the top level, right? But then the way that it's set up is so now the red nuts are supporting the top platform and everything below it. Because everything below it is hanging from that top platform that's being supported by those nuts. Does that make sense?
Yeah.
Thus the problem. Cool? So I think if you understand that, you're in good shape. Alright, cool. Alright. Last one was number 16, the stupid insect legs. There were slim pickings for problems from this section. Yeah.
Insect legs is pretty boring, but like catwalks and feathers, so long. It's like insect legs.
Say that again.
It's kind of boring for like patients and parties.
Oh, right, I got you. As compared to this, yeah, totally. All right. I'm just trying to decide if we have time to go through it, but I think we do. We got 10 minutes. Okay, so here we go. We've got a rod. So this is, what are we in? Section 5.2, number 16. All right, so we've got this rod, and then there's a little bug hanging from it. Oh. No, we need to, oh, he does have antennas. Okay, so there's the bug, right? All right. Oh, looks bad. Sorry. I think it says, doesn't it say that you're supposed to assume that the legs are horizontal? Yeah, the leg sections nearest the body are horizontal. Yeah, that's important. Okay, so let's see. What do we know? We know that this angle here is, I'll just write it here. Theta is 40 degrees. It's got 6 legs. They're all under the same tension. Leg sections nearest the body are horizontal. The insect has a mass of M. What's the ratio of the tension in each tibia, the fore part of the leg, to the insect's weight? So, let's do this. So the force of gravity on our bug is just going to be his mass times g, right? All right. Now, what's holding it up is each of the legs, right? Now, there are 6 legs, right? So that means that each leg is indirectly responsible for a sixth of this, right? So if you look at one leg, here's what you've got. So here's the force in the, how do they describe it? The tibia, is that right? What is the ratio of the tension in each tibia to the insect's weight? So I'm looking for the force in the tibia. for the weight. So I know that this angle here is 40 degrees. And I know that the force in the tibia, the y component of that, has to be a sixth of this. Follow? So, let me double check my notes here and make sure that this is that I'm not overlooking something dumb like I did in that other problem. I think we just got to find FT using some trigonometry. Yep, that'll do it. Okay, so we want to find FT, right? So, what's a sine? So the sine of 40 degrees is FT over mg over 6, right? Nope. I have that upside down. Opposite over hypotenuse, not the other way around. Mg over 6 over force of the tibia, right? This is a 6. Cool? All right, now what ratio are we trying to find? We're trying to find the ratio between the force of the tibia and the weight, right? So I want to rearrange this to get Ft over mg. Follow? All right, so I'm going to multiply both sides by 6 to get rid of this. So I get 6 times the sine of 40 degrees equals the weight over the force of the tibia, but I want the reciprocal of that, right? So that means 1 over 6 times the sine of 40 degrees is the force of the tibia over that. Because the way the question is worded, the problem says, what's the ratio of the tension to the weight? Right? Mg is weight, right? And tension is my Ft. So that should give you 0.26. Good? All right. And then part B just says, if the insect straightens out his legs somewhat, does the tension increase, decrease, or stay the same? Well, if he straightens his legs, that means that more of his force becomes vertical component and less of it's horizontal. So that's going to decrease the tension, right? Like, it's easier to hang from bars like this than it is like this, right? There you go, right? That's why. Cool? All right, questions, comments? All right. This is up to 5 minutes. Why don't we do either 60 or 61? Let me do 61. I'm going to jump back a section real quick because we have time. Let's do 5.1, number 61. I think we have time to get that one in. It's really just some algebra. Sorry to jump around. Okay, so 61 says a hot air balloon. Oh, no. Oh, 83 isn't even on the list, is it? Have you guys write in a different color? 16, 61. Okay. This isn't the one I was thinking of, but okay, let's do it. I don't know if we'll have time. All right, so here we go. So it's a hot air balloon of mass M. So here's our hot air balloon. It's got a mass of capital M. It's descending vertically with a downward acceleration of magnitude A. So there are two forces on this thing. There's gravity pulling it down, and then a mysterious lift force. We don't know how much lift force there is, right? All right, and it tells us that because of this, it's accelerating down with an acceleration of A. So look, negative A, assuming A is a positive number, negative A is going to be the weight minus the lift divided by the mass, right? Make sense? All right, now, the question is, how much mass M, lowercase m, do I need to take out to make it accelerate upwards at a positive A? Okay, so now we've got our same balloon. but now its mass is capital M minus lowercase m. So our force of gravity now is m minus m times g. Here's our lift force. And so now we get A equals mg minus, nope. Yeah, we're not going to fence this. All right, so, yeah, we didn't have time to finish this. I was thinking this was a different problem when I started it. So, but let me pause for a minute, because as we go further into this, you guys, this is going to happen more, where you're left, like you've got no numbers, literally 0 numbers here. You've still got to solve the problem, right? That's going to happen more and more often. All right, now, when you do that, I had 2 people asking me about this at various times in the last couple days. When you do this, when you're trying to solve, but you aren't given any numbers, you need to write your answer in terms of the variables you're given. All right, so the variables that we were given were A, capital M, and lowercase m, and then obviously G is a constant, so that's legal. All right, so you need to solve for lowercase m in terms of those other guys. Does that make sense? All right, I'll solve this one online and throw it up on the website. All right. 5.3a is due on Thursday. We got more notes on Wednesday.